So I'm thrilled to be here in Osnabrück. I've heard about the cognitive science program here for many years. I've never been. This is my first time in Osnabrück, and I'm blown away by how much cognitive science is going on here. So thanks for having me. Please interrupt me while I talk. That's the whole point for me being here, rather than Skyping in or something. So the more interactive it is, the more amusing it is for everybody. So I'm going to be talking about concepts. Why is concept learning important? Why are concepts important? If you buy researchers like Stephen Harnad, almost everything in cognition has to do with concepts and categorization. Whenever we're doing disease diagnosis, whenever we're engaged in object recognition, prediction, identification in our worlds, whenever we use words, when we say, hey, glasses or computer or laptop, we are engaged in the world of concepts. Wittgenstein, the philosopher, argued that we're constantly in the process of not just seeing our world, but seeing it as something. So we can't help, when we look at the bottles over there, to see them as bottles rather than just seeing them in some raw, semantic-less way. So a general account of categorization would be wonderful if it's possible. It would be valuable to many, many different worlds, which is why so many people have pursued it. It's maybe a sign that people are so interested in these generic counts of categorization that we oftentimes use representations like this. I don't want to pick on my old advisor, Doug Medine, but what he's doing is very common in the field, which there's actually stimuli here. I think they were rocket ships originally in this study, but nobody, at least Doug, was not interested in rocket ships per se. He was interested in categorization behavior in general, and so he just automatically translated the dimensions of the rocket ships into ones and zeros. One might be a round versus a straight edge for the fin, right? And so you can see right off the bat that there's a huge interest in saying we're interested in a generic account of how we learn all of our categories, right? Why? It would have a huge payoff if you're interested in art categorization or word categorization or disease categorization. It would apply to all of those. Is it possible? We actually don't even know the answer to that. It could very well be that all categories are not alike, that there isn't going to be a generic approach that will allow us to explain all of our categories. Is it nonetheless worthwhile pursuing one? I think it is, because the payoff would be so huge if we can account for even some portion of the variance in our categories. So I'm going to be, because I think the field does, focusing quite a bit of the time on artificial categories, because that's what a lot of cognitive psychologists do. But I will make a tip of the hat to real categories oftentimes, and what is the connection between these artificial and the real categories. The picture of the rainbow is just to suggest that this dealing with categories is something that we engaged in unconsciously, automatically, without thinking. We see a rainbow that we have every reason to believe from the physicists have every primary wavelength of light in them, going from red to violet, but we naturally see it in terms of categories: red, orange, yellow, green, blue, indigo, violet. So that tendency to turn our continuous raw world into these discrete bins, that's what I mean by categorization. Why do we engage in this? Part of the reason is communication. When we communicate with one another, we use concepts, and that allows us to communicate in a very efficient way. I can say that my friend Ben is a professional American football player. And as soon as I tell you American football player, I'm conveying a huge wealth of information about his proclivity to violence, about his possible steroid use, about his athleticism, etc. So when we use these words, we are buying into the concepts that underlie those words, and we're able to communicate efficiently. So every time you use a word, there's a concept. There could be concepts that we do not have words for, like those plastic things on the ends of your shoelaces. Anybody know the words for that in English? That would be aglet. No, there. Don't say you haven't learned something already. So aglets are those plastic things. It seems like Germans have a word for everything, right? Beautiful example of metaphoric extension from the German compound words. Beautiful, right? We could give lots of examples, but just earth nut, isn't it beautiful? Erdnuss, right? I mean, I guess you just use it all the time. It's a peanut, we would call it, I guess. Kratzenkraller? No, Wolkenkratzer. Wolkenkratzer, right? Beautiful idea of I guess we have the same idea, I guess, in English. Skyscraper. I guess a cloud scratcher, maybe, right? Or glue burner, right? Right? Beautiful. Glue burn or glue burn? Yeah, a glowing pear, right? For a light bulb. So yeah, you can see a lot about the nature of a community, of a culture, by way of its metaphors of when explaining something new like a light bulb, and trying to explain it in terms of things they already know about, like glowing and pears. So another thing that concepts do is they allow us to conserve space. They allow us to compress our world informationally. And here the important notion is equivalence classes. So I think a big part of what concepts do is they say, for our current purposes, we're going to treat all of these different things as cats. We know that no two cats are alike, but we're going to treat the cats for some purpose as being equivalent. And that notion of equivalence sets, I think, underlies a huge portion of the information compression benefit that we get from concepts. They also allow us to build up more elaborate thoughts, like, I guess, glowing pears, right? Fruchtwasser, another good example, right? But fruit water, but I guess it's amniotic fluid is what we would call it in English, as a baby is developing inside the mother, right? So as soon as you have a concept, then it can engage recursively in the building up of more advanced concepts. Oftentimes, it's going to be hard to see what the extension of that concept combination is just on the basis of the intentional semantics of the individual components. There has to be some connection between the external world and the compound, right? A lot of work in cognitive psychology is in the world of conceptual combination. What happens when two concepts combine together to figure out what they're going to mean for the entire object? Another huge thing that concepts do for us is prediction and generalization. By many accounts, I think by the Bayesian accounts of Tom Griffiths and Josh Tenenbaum, this is the primary reason for our concepts, is because it allows us to make inductions. So we come across a rattlesnake in the Arizona desert, and it is our conceptualization of rattlesnakes that allows us to avoid it, right? Are we being biased? Yes. Are we being prejudiced? Arguably, yes, we are being biased and prejudiced, but it's a good kind of bias to have that will allow us to stay living. in this case. So we do not know this particular rattlesnake. This particular rattlesnake may be kind and gentle, but it's probably a good bet that it's like other rattlesnakes and it can kill us. Right? That is an inductive generalization. I guess from a social psychology perspective, the purpose should be to try to come up with generalizations that are accurate rather than just like skin deep. But I think we are all engaged in the process of creating generalizations. Okay. So a big part of what I would like to be talking about for the next couple of days is different proposals for how we're representing our concepts. And I'm breaking this down into maybe 5 or 6 different theories. I won't spend equal amount of time on all of those, but it'll be a good way of organizing what I think is the lay of the land, at least from cognitive psychology. I have them roughly organized, very roughly, according to time, where the stimulus-response association accounts were some of the earliest accounts of how we learn concepts, dating back to the 1920s, if not before. Then along the 50s, the early 60s, really the birth of cognitive science as I know it as a field, and rules came to the prominence as a way of representing concepts. Then the freewheeling 1960s, early 70s, people didn't want to be living under rule systems anymore. That was the heyday of concepts as prototypes that not coincidentally had its start in Berkeley, California. Exemplar models, category boundary models, and concepts as theories is what I will be talking about. I will put these slides, by the way, online, hopefully today. Okay, so that's the overview. I guess just diving right in, talking about concepts as associations, I think had it start with the behaviorists of the 1920s, and their argument was we learn concepts the way we learn everything else, through creating associations between stimuli and responses. And a lot of the experiments had to do with subjects, these are human subjects in this case, trying to learn particular responses like ooh, yer, li, to give when presented with these made-up Chinese ideographs. So the stimuli that a subject would see would be the stimuli in this 6x6 matrix over here. So the subjects would see these stimuli here, and when they saw this stimulus here, they would be asked to say, what is the correct response? And the subject would respond, I've got no idea, you haven't told me. And the experimenter would say, play my game. Right. So they would say, I don't know, is it a ta? And the experimenter would say, bah. And they would give them the correct response, which is ooh. Okay. And so then a subject might see this one, they'll say, ooh, that's the only thing I know about. And they said, no, actually that's a year. Gradually over the course of 36, 50 trials, the subjects would be able to learn to make the correct response. Right? And interestingly, according to Hull, they were able to make the correct response even though they had not consciously been able to identify what was the defining feature that made something an ooh or made something a year. What are these defining features? Well, all of the oohs have this check mark with the 2 sideways flying seagulls. And all of the years had this particular pattern in it. So those are the defining characteristics, and subjects were certainly able to get over 50% correct without being able to identify those characteristics. And so Hall talked about there being an automatic association learning process where you would take visual features like this check mark and you would associate it with this response that you're supposed to give, the ooh response here. And that is what category learning is. And the reason why I'm mentioning this a little bit is because this seems kind of primitive and coarse, but you could easily argue that a stimulus to response association model is behind the huge amount of enthusiasm in machine learning now with neural networks. In particular, the best system for recognizing images, for example, is based upon a machine learning method involving what's called deep learning networks, in particular convolutional neural networks. And unlike the original Hall view, these networks have multiple layers. So there's a single input layer, which is just pixels on a screen, and the output layer is going to be an image classification. So for example, it would say, oh, that's a bottle cap, or that's a German Shepherd, or that's a Persian cat. So those would be the outputs. And unlike Hall, you're imagining that there's a number of hidden layers that can fall between the input and output. Using tricks developed in the 1970s, there's going to be a back propagation of errors. So when you give a particular response, you're shown a bottle cap and you call it a German Shepherd, you're told the correct teacher signal for this image would be bottle cap, and you figure out what would have had to have been the weights from the last hidden layer to the output in order to get you closer to saying bottle cap, and you back propagate what is the state of all of the hidden states in order to get to the next state after that. And so we know from the work of like David Rumelhart how to mathematically make precise that notion of creating the weights that will allow you to create the weights that will allow you to create the weights that will eventually give you the output label. There's been a couple, actually surprisingly few, but there's been a couple of real innovations compared to the back propagation networks of yore. So one of the important ideas, and this is really a repeating motif, I think, in machine learning, is that you oftentimes get better learning outcomes if you put more constraints on the learning algorithm. That there's something called no free lunch theorem, which basically says that you can't have a system that can learn anything efficiently. The ways to get it to learn in an efficient way is to have it be constrained to learn about the kinds of structure that the real world actually provides to you. Okay? And in that world, one of the important constraints of these networks is that there's going to be two important constraints, really. One is a spatial constraint, that it will tend to create features of its world that are spatially compact features. It won't consider creating a feature for a pixel all the way over here and a pixel all the way over there. It'll create these filters, these features that are going to have compactly, spatially related pixels to each other. The important other kind of constraint is that as it's pulling out these features from the patterns that you provided in the world, it's going to be assuming that those features are applicable throughout the visual world. So that if it pulls out a particular line segment as being a repeated regularity in the world, it's going to replicate that line segment all over the world. And that will give it something that we call translation invariance, so that if you recognize a cup over here, you'll also, for free, be able to identify the cup over here because of this weight sharing protocol. Other kind of clever advantages of new applications of deep learning compared to the earlier ones is this idea of coarse coding, that overlapping receptive fields for higher layers. So you might have thought you'd have a better neural network if you had very clean-cut discriminations, that I'm just going to respond to this area, you're just going to respond to this area. But actually, by putting overlapping receptive fields in these neural networks, you can actually achieve far greater sensitivity. So the way the most impressive convolutional neural networks work these days are, well, here are some of the techniques they're using. One of the ideas that's been discovered recently is you can go through the weights in your neural network and you can systematically drop them out. And what this avoids is having one weight pick up too much of the input and try to handle the whole categorization by itself. If you want to have your networks so they're not likely to overfit, just be able to account for the stimuli you show them without being able to generalize to new stimuli, that's important to use this dropping out technique to avoid the overfitting, as it's called. So all that you do when you're training the system is you train the system by presenting these millions and millions of ImageNet images, and then you'll say, on this one trial, we're going to turn off this subset of 5% of the connections from one hidden layer to another hidden layer. What I'm showing you in this picture is a convolutional network, which I was saying was taking advantage of the spatial structure of the inputs. So let me see if I have another. So yeah, maybe this is a better overall diagram of a convolutional neural network. It is going to be creating these basically different features that it's pulling out in the input patterns. And so a lot of our world, for example, has straight lines at different orientations. And so that would be a natural feature for these convolutional neural networks to pick up on. They're going to be picking up on these patterns at multiple scales. So not only teeny tiny edges that make up this object, but bigger bars if our images are going to have long bars as well. But there is no constraint that these features have to be bars. If you show the convolutional neural network a whole bunch of donuts, it'll pick up on round features too, right? So in convolutional neural networks, you actually are going to be interlacing two different kinds of networks. One kind of network is going to be trying to create these features that it detects as statistical regularities in the input patterns. And the other kind of layered network, which is going to be swapping in and out with this kind of network, is a reducing network that will say, we're going to try to create compressed representations such that all of these feature detectors in this particular part of space are going to be projecting to just one unit at a higher layer. Right. And these are called pooling layers. And what this is going to do is it's going to end up with a more compressed representation of your inputs. And so it fits in a very satisfying way with what we know about the early layers of visual cortex. And Dan Yammans from Stanford has written a lot about this. Similar to the early stages of visual processing in the cortex, there's a largely pyramidal structure, so that the most peripheral visual cortical network neurons are going to be responding to very small line segments or very small pieces of the stimulus that are going to be located in particular fixed areas in visual space. Whereas if you go deeper and deeper into the cortex, you're going to be having neurons that are responsive to larger and larger parts of the visual world. Right? So making this a little, so you see this, I think. So this is the actual input. These are early layers in the convolutional neural network. These are going to be later, and these are going to be even later layers. And what you can see is that you end up going from fairly micro, teeny little pieces of the world, and the world gives us things like straight line edges, really, to what you might call holistic representations of the entire form of different cars. And that is very common kind of organization. So in a way, deep learning models are really very neatly cutting a huge contention in cognitive psychology between analytic and holistic representations, right? So there's a whole debate for several decades on whether we represent objects holistically by comparing them overall to images, or whether we recognize objects by breaking them out into small, teeny pieces. According to convolutional neural networks, the answer is yes. Right? We're doing both. The earlier layers are breaking down the input into small little pieces, whereas the later parts of the network are representing entire cars. Interestingly, if you feed in a convolutional neural network with different kinds of objects, like faces here, cars, elephants, and chairs, what you'll generally find is that the early layers of the network are going to be very similar to each other. All of them are made up of lines, really. And it's no surprise that every mammalian visual cortex, if you look in the primary visual regions, will also have these line detectors. There will be neurons that will respond selectively to, for example, a line at 45 degrees, but won't respond to a line presented to it at 50 degrees. Right? But if you go up, ascend the layers in the convolutional neural network, then you'll see that there's differences between the networks that will create for faces, cars, elephants, and chairs. And then at the highest layers, you'll have even more differentiated representations. This also gives rise to a huge new area of research in machine learning, neural networks, called transfer learning, where you're interested in, if you train a network with some kinds of stimuli, how well will it do on other kinds of stimuli? And in many cases, the answer is it'll do surprisingly well. And you can see right here, one reason why that is because you could train a system just on faces, and to the extent that cars are also going to use the same low-level visual cortical representation of lines, you'll get some savings for processing cars by proceeding with something that's completely different, like faces. Okay, so this is all just to say that we have this quaint response to stimulus-response association models where we say, oh, wow, yeah, I guess we have to know about them for historical reasons, but none of us are behaviorists anymore. And to that I would respond, no, that's not right. Some of us are still behaviorists. There's many senses in which the deep learning craze individuals, the researchers, are very much following a line of research which I think is continuous with behaviorism. Now, of course, the huge difference is the behaviorists, some of them were, but a lot of the behaviorists weren't talking about all of these hidden layers, right? So these are intermediate level representations that the machine learning theorists put well, they don't put them, they have their system learn so that they can pick up on the regularities at multiple spatial scales of a given set of like 1 million images, right? So that is true, not all of the behaviorists, but some of the behaviorists, even back 50 years ago, we're still talking about the need to create these hidden layer, latent learned representations. But I think it's something that certainly all modern behaviorists, machine learning theorists would require. So these are super important. If there's going to be regularities in inputs at multiple levels, then you're going to be dramatically increasing your efficiency of learning by learning those regularities. And that's what they do. A lot of work in modern machine learning is getting advantage just by virtue of increasing the number of layers. For several years, the best systems for automatically tagging ImageNet representations were achieving their superiority just by adding layers. So now I think they're up to, I don't know, what is it, 26, 37 layers going from the inputs to the outputs. Okay, so yes, that is still one major approach to concept learning, at least from a visual world view. I'd like to transition now to what I will call the classical view that I will blame on Jerome Bruner, circa 1956. And here, I think very much in the back of Bruner's mind was something like, oh, those behaviorists were awful. You know, they kept on talking about just like this sort of passive creation of these stimuli to response associations. And that was very much shown by like the Hall Chinese ideographs, right? Even though you didn't even know as a subject what made something be an oo or a lur, you were able to learn this through these stimulus response associations. But in the 1950s, cognitive psychology comes along, information processing. The idea of an active learner becomes very important, that there's a person looking at the stimuli, trying to make sense of those stimuli, trying to create what are the rules that generated the stimuli that they see. And so Bruner argues that concept learning is an active process of trying to create hypotheses for the structures that the observer is seeing, and then test to see whether those structures are in fact right. So according to Bruner, then, learning a concept means finding the correct rule for determining whether something belongs in the concept or not. So concepts are going to be represented by rules. Oftentimes, at least in the early work in concept learning, these are rules that are necessary and sufficient. I guess you would say individually necessary features and jointly sufficient, so that if you have all of these features, then you're sufficient for being in the concept. And what the early cognitive psychologists did were they give people different types of rules to learn, like a conjunctive rule. You're in the category if you're square and striped. A disjunctive rule, like you're in the category if you're striped or square. Or a conditional rule, this is like an if-then rule. Do I have this right? If square, then striped. I think that's right. Can somebody confirm? So what the only things that shouldn't... Oh, no, I think I got it wrong, right? It's more like if striped, then square. Because these things over here, they meet the precondition, they're striped, but they're not square. So they're verboten, right? Yeah. So these are the different rules, and Brunner was very interested in how difficult it was to learn these different rules, how many trials it would take. In an active hypothesis testing way, he was very interested in the stimuli that the subject would uncover themselves in order to try to confirm or disconfirm the rule. One of the interesting results from Brunner that I think modern cognitive psychology hasn't really adequately addressed is how hard it is for people to keep in their mind simultaneously multiple hypotheses. So Brunner, for example, showed, I think pretty persuasively, that when somebody was investigating a particular hypothesis, like if striped then square, then they could go about trying to confirm or disconfirm that, usually trying to confirm it rather than disconfirm that rule. But they were getting very little evidence with respect to other rules, so that if they were wrong, it was very hard for them to then consider adequately all the previous items that they saw to come up with a new rule. This is something that computers can do far more efficiently because they can just store all of the items in their memory. But people seem to be very rule-specific in their contemplation of the evidence. Okay. So this is what a lot of the early work in the 50s and 60s was about. I want to jump for a moment to problems with the classical view. So the classical view, I think, is definitely has one notable advantage over the behaviorist accounts, namely that it really does say there's an active contribution of the person rather than just a passive creation of these stimulus-response associations. Going back to philosophers like Wittgenstein, it's very difficult to find what would count as the defining features for many of our most beloved concepts. So his famous example was game. You can't give me a definition of a game that will exclude war, but will include Frisbee, maybe. And so he was arguing that you should not be looking for a single definition of games, and this is true even for philosophical concepts as well, which is more controversial among philosophers because they love definitions, of course. There's also the problem with unclear cases. So I'm distilling lots and lots of experiments here, but there was a number of experiments showing, I associate them with like McCloskey and Glucksberg, that people disagree with each other about what the categories are. We might think, you know, if our human categories were rule-based and we knew what those rules were, an important if, I guess, then we should agree with each other. And yet, in many experiments, it turns out that people do not agree with each other about many categories. Even worse, according to McCloskey and Glucksberg, is that people oftentimes will disagree with themselves. So if you ask people from one week to a next week, is a crab a fish? People will say yes one week, no one week. I know they're not fish, but they live in the water. It's confusing. If you ask people, is a bat a bird? Many people will disagree with themselves. Is a camel transportation? Kinda yes, kinda no. They will disagree with themselves, and even in the situations where they agree with themselves, they have no problems with coming out with different typicality ratings. So people will say, well, look, I know that a flamingo is a bird, but it's a really bad bird. I don't mean in a moral sense. I just mean it's not a very birdie bird. So people disagree with each other and themselves, and even when they agree, there's a natural typicality gradient for objects, how good a member they are of categories. Penguins, robins, both birds, but robins are definitely the more typical. Now, I have to say, in the same way that deep learning has really resuscitated a lot of associationist ideas about concept learning, there has been a renaissance, I believe, an important renaissance in rule-based views of concepts. And this is by way of the Bayesians. I'll put in this group Charles Kemp, Noah Goodman from Stanford, Josh Tenenbaum from MIT, Griffiths now at Princeton, right? They have an interesting take on categories as rule-based in a way that gets around some of these problems with typicality and unclear cases. And they do it in a very interesting way by making categories the integration over many, many possible rules in a probabilistic manner. And I think the best way to give you a feel for what the Bayesian account of generalization via concepts is by going back to some of the earliest work on this by Tenenbaum and Griffiths. Here's the simplest example of this. You have a Bayesian system, and you tell it, hey, look, there's an item which is, 60 inches long. And I'm telling you that it is in the category. It's whatever. If you click on it, then you'll get a little bit of Purina pigeon chow. I don't know if you're a pigeon. So the 60-inch object definitely is in the category, and that's all you know. According to Tenenbaum and Griffiths, what you engage in from a Bayesian perspective is all of the possible rule-like hypotheses that could generate that result. And the only result that we have so far is 60 is in the category. And what are some of these hypotheses? Well, one hypothesis is that you have to be exactly 60 to be in the category, and nothing else belongs. They also consider the hypothesis, well, maybe anything which is 59 or 60 belongs in the category. Or there's another hypothesis which also has a size of 2, which is that anything which is 60 or 61 belongs in the category. Then there's a number of size 3 hypotheses, like anything from 58 to 60, anything from 59 to 61. So those are all of the different hypotheses. Yeah?
So all of those hypotheses assume that we always have intervals.
Compactness.
We have 55 and 60, but everything in between.
That's brilliant, yes. And that is super important. And that is analogous to this in the convolutional neural network, I think, about this imposition of this idea that you have to have compact features. You don't have a pixel here and you don't have a pixel here as a single feature. And so, and that's where the no free lunch theorem, I think, is kicking in again. If you don't put in something like that compact range constraint, then anything goes. If you don't privilege some kinds of hypotheses over others, then you won't be able to get any kind of efficient learning system. Certainly in their case, they do. Now, of course, it naturally occurs to people, well, I could easily think of a category that was like all of the even numbers, 60, 62, 64. You can put those in. You have to have a way of generating those kinds of hypotheses. And so there are hierarchical Bayesian models that allow for the construction of a hypothesis space from fairly minimal structural assumptions, like I'm going to assume that my features are basically following in a tree, or following in a chain, or an array of features. This is the work that was in Proceedings of the National Academy of Science by Charles Kemp and Josh Tenenbaum. And they were able to say that you could start off with very high-level assumptions, that there's different kinds of structures out there, like chains and arrays and dimensions, and that can suffice to learn categories. But yeah, I think basically I'm completely in agreement with you, and I would say somehow or another, I think one of the things that we learn from cognitive psychology is well, I'll blame computer scientists. There's something I'll call like a second-year graduate student computer science fallacy. The first year, they're too busy taking coursework. But in the second year, they say, okay, we're going to be starting to work on our PhD. And they just say, okay, we're just going to show a very blank slate, tabula rasa neural network, just thousands of videos from YouTube, and have it create all of the structure. It'll create cats and dogs and people and whatever are the categories that are in the YouTube videos, and it will do so without any pre-training. And I'm calling that a fallacy because I think, as you were pointing out, if you don't put in some kind of constraints on the learning process, you're not going to get efficient learning out. Now, one of the, I think, real ongoing interesting questions in cognitive psychology worth a couple of PhDs out there is, to what extent can those constraints themselves be learned, right? And so this is a major approach, both in the Bayesian worlds and in the deep learning worlds. They're trying to get systems that will themselves learn the constraints that they will then use to do future learning. In the world of deep learning, this is the world of transfer learning that we've already talked about. And in the Bayesian world, this is hierarchical Bayesian modeling. And in hierarchical Bayesian modeling, you're able to learn to make hypotheses at multiple levels. So to take the example from the philosopher Nelson Goodman on learning over hypotheses. What Nelson Goodman says is, you know, you come to an island and you see it has a whole bunch of weird four-legged animals that we would otherwise know as llamas, and it learns that all llamas have four legs. It goes to another island and it sees that all of the storks there have two legs, and it can learn that all storks have two legs. Now, it comes to another island and it sees a single ant, and it has 6 legs, as ants do. The formation of a over hypothesis for Goodman is the hypothesis that every animal of a particular species will have a characteristic number of legs. That's an over-hypothesis. It's not an hypothesis at the level of, I think ants all have 6 legs. It's saying, I have learned through my experience of animals in this world that the animals that belong to a common species all have the same characteristic number of legs, whatever that is. Right? So I'll leave that to be a variable. But once I come across now a single ant, if I've learned the over hypothesis, then I'll be able to generalize fairly rampantly to think that all ants have 6 legs. Right? And so right now the Bayesians have a accepted account for how you can learn these over hypotheses in a hierarchical framework where you're both learning specific level hypotheses like llamas all have 4 legs, and you're also learning these over hypotheses about species having characteristic numbers of legs. And in one way or another, there's also increasing work in that in the deep learning world. Yeah, great. Yeah?
So all of these hypotheses are not equal? I mean, they're all, I guess with Bayesian, they're proposing these, but as you're talking about the overgeneralization, it seems like the bottom ones are more likely?
Yeah, so that's interesting. They are not all equal for Tenenbaum and Griffiths, and they have what they call the size principle. So yeah, so they're only assuming these compact ranges of hypotheses, and they say that there's more weight to the more restrictive hypotheses. So as we go from size 1 to 2 to 3 to 4, they get less and less weight because they're too unrestrictive. Basically, you could have an hypothesis that was infinite long, and it would basically say everything belongs in the category, but it's not very diagnostic. So they say that there should be a preference for these over these, then. Yeah. And so, so one of the advantages I wanted to mention about the Bayesian framework, though, is it has a very natural way of saying that if you have more data, but you have more data from the same range, then the generalization naturally should get sharper and sharper and sharper. So if we have one object at 60, basically the system will create these sort of concave, quasi-exponentially decreasing generalization curves that you see up there. If you presented 2 objects, one at 52, one at 60, and you do this integration, weighting the hypotheses so that the smaller ones count more, then you'll end up with a generalization that looks like this. And then if you have a whole bunch of data going from like 50 to 60, this is what the generalization gradient of a Bayesian system looks like. And you can see it's quite tight. It's pretty sure that if these were a random selection of objects that belong in the category, it's pretty damn sure that, that this category doesn't include things that are 80. If things that are 80 had been in the category, then it would have been very unlikely that they would not have been sampled, right? And so that's what's going on in the Bayesian account of categories. This is a good time for other questions. Yeah.
Yeah, I'm a little more concerned about the cognitive plausibility connecting these whole learning happens and what actually happens in human brain. So kind of when we see concepts, when we categorize concepts, do we behave exactly like in these learning or machine learning networks that we don't know how they act exactly? I mean, I'm fine with the black box of machine learning, no problem, but is there a connection between what happens in this learning process in machines and what happens in the learning process in the cognitive?
So that's a great question. It's going to be very complicated to answer, and I don't know how to get outside of my own skin in answering that, but I will try to channel my inner Tenenbaum and my inner Botvinnik and Hinton too in answering that, because there's both. It's very much something that we could discuss. I think it's the most important question, and I think there's weaknesses and strengths of all of these systems with respect to their application to humans. So on the Tenenbaum side, he says, look at the deep learning systems. They require so many more inputs than we require. And so there's a very nice behavioral and brain sciences article that just came out maybe 1 or 2 years ago by Brendan Lake and Tenenbaum and Goodman and all those people. And they were basically arguing exactly that deep learning systems are incredibly cognitively implausible because of the number of training instances that they require. They make very strange errors. Sometimes you can change a pixel in what would ordinarily be a perfectly good llama picture, and it will miscategorize it completely. Whereas you would look at it and say, it looks like a completely good llama to me. You have to pick the pixel. So this is in the world of generative adversarial networks, where if you were to change just one pixel, that would suffice to dramatically decrease the deep learning system's accuracy. So that is bad on the deep learning side. On the positive for the deep learning side is you get this very nice correspondence between how the visual cortex is laid out and the layers of the deep learning. And it captures this idea that you don't have to start with a system that has these features built in, like the hypothesis space is built in for the Bayesian accounts, and yet it can be learned. And it can transfer to varying degrees of efficiency to new materials. The deep learning systems do not have to have structurally complex models to represent the hypotheses. It will, in a very piecemeal way, be combining evidence for lots of different features together to create the categorization. Now, the problem with the Bayesians, from my perspective, is that they require, in some way or another, that people are keeping in mind many, many different hypotheses, and they're integrating over all of these hypotheses in coming up with their eventual accuracies, their categorization accuracies. And you can see this very well right up there, that it's as if the system is considering this hypothesis and this one and this one and this one, and then not only is it considering all those hypotheses, it's integrating over all of those hypotheses and their prior probabilities to come up with a posterior probability for a hypothesis given the data. So it's Bayesian because they're trying to figure out what is the probability of a given rule given the data that I've seen. Maybe I only saw one thing at 60. What's the probability of different hypotheses? And good Bayesians that they are, they calculate that by calculating what is the probability of the data given each of these hypotheses multiplied by the probability of the hypothesis, divide by the probability of the data. That's what they say. But in that second, on the right side of that equation, if I put it up, you would have had to have all of the probability of the data given each of the hypotheses. And that is a cognitively implausible task, in my opinion. And that's why I was mentioning before that Brunner was very interested in this active hypothesis formation strategy, where you'd only entertain one hypothesis at a time, because people have a hard time keeping in mind multiple hypotheses. So I would say that each of them thinks that their systems are plausible. To me, it seems that I buy both of when they say there's implausibilities with the other systems. I actually buy both of those. And it leaves me dissatisfied, which is why you guys are needed in the future, because you are the next generation of cognitive science. And I would say one of the things that you should be tasking yourselves with is to come up with psychologically plausible accounts of model-based categorization. So the deep learning systems are not properly model-based in a way. This is really clear from the AlexNet representations that, at least back in 2016, they were the best computer-based image classifier system out there. And they were very good at being able to say, oh yeah, there's a Doberman Pinscher in this image. Now, if you go on to ask them, okay, where is the ear of that Doberman Pinscher? I got no idea. Where's the nose? I've got no idea. They don't know where any of the parts are. They're able to do the overall categorization. In that sense, I think they're very unnatural, psychologically speaking. For us, it is the same pattern recognition ability that allows us to say that this is a Doberman Pinscher, that also allows us to say where the nose is of the Doberman Pinscher, right? And so there is a sense in which these deep learning systems are very unstructured, right? And so I think that's a huge problem. But that does not mean that you have to bring out the heavy horses of Bayesian reasoning and probability integration of lots and lots of different hypotheses. So what I task you with then is coming up with a learning system that is actually more model-based, that is imposing models onto the world it's seeing, but at the same time it's doing it in a more lightweight system that is actively postulating one or two models without having to postulate millions and millions of possible hypotheses. I think that would be a very exciting way to go.